Okay, so thanks very much for the invitation. I'm very happy to be here, especially this event to celebrate Deepak's Boltzmann medal. And it's great to be back in Bangalore and India in general after all this time. Okay, so loudly. Okay, so I'm going to look at the problem of diffusion in a channel. So you can think about this as a simple model for a porous medium or something like this. So you can imagine in a two-dimensional case, you can just think of having a Brownian particle. Okay, I'm looking at Brownian motion in this channel, and it has two surfaces, one at given by y equals h1, and the other given by y is equal to h2. So here the bottom of the channel is flat, and the top of the channel is undulating. I'll be interested in periodic channels, okay, for the techniques I'm going to apply. So I'm just going to look at basic Brownian motion, and I can put some sort of uniform drift along the channel if I want to. So this is just the basic diffusion equation. So physically, what I've got is Brownian motion, and when it gets to one of these surfaces, it's just reflected, and in general, there's no flux boundary condition. So nothing really interesting happens. It just stays in here. And obviously, I mean, in more realistic systems, I would have variations in the diffusivity due to the surfaces. I'll talk about that later. So it's a very simple problem. Of course, this is just the no flux boundary condition. This is the current here, okay? So the question is, so if I just looked at one of these periods, everything looks very simple, okay? If I just look at what the diffusion does, if I put periodic boundary conditions, I'll just eventually at late times just get a uniform distribution here. So it looks as if something completely trivial is happening. But actually, if I then decide to look at how this particle goes along the channel, how is it going to diffuse in this direction here? So if I have a porous media, I have some sort of pollutant, I want to know how quickly it's diffusing here. Actually, the problem becomes non-trivial because of this, it's not going to diffuse freely, because you can see that in certain cases, I'm going to sort of, here I'm being reflected. So my dispersion is going to be slowed down by the presence of these traps. Now, these traps look quite shallow at the moment, okay? Okay, so this is, and as I said, in general, we can have fluctuating surfaces at the top and the bottom. Okay, I'm going the wrong way. Okay, so actually there's an interesting calculation you can do. If you just try and calculate the marginal probability distribution function for the position x along the channel, so you want to integrate over the height direction. So you're only interested in how far you're going on. And so if you put this into the original equation, actually, you actually find that the marginal distribution actually has a diffusion equation. Now, this is just the Laplacian parallel to the channel. You have the same drift term as you had before, but unfortunately, what you actually find is these extra terms here, which depend on the position, actually, the probability density function, the full probability density function for x, but actually measured at the extremities, okay, at the top and the bottom of the channel. So actually, you don't have a closed equation for P star, okay? So it's a bit disappointing. So actually, a long time ago, people came up with which is called the fixed Jacobs approximation. So physically, if you imagine, if my channel isn't undulating too quickly, so my diffusion is very, so my process can equilibrate in the y direction, okay, while things are not changing too much in the x direction. And so you can basically assume, just make the physical approximation. Oops. Okay, yes. Sorry about that. Okay, so you basically assume that it's equilibrating in this direction. And so basically you can see this from the diffusion equation. If you scale the diffusion equation in terms of L, the distance along which it's varying, and the height, you can actually, basically do what amounts to in fluid mechanics is called the lubrication approximation, okay? And you can also put yourself in this situation in a more artificial manner if you imagine that the diffusion is much quicker in this y direction than it is in the x direction, okay? So you can find concrete examples where this can happen, okay? So the thing is, and obviously it's obvious that you're not going to get a closed diffusion equation here, right? Because, x, just the process along the channel is clearly not a Markov process, right? So this would be a miracle if you could actually write down an equation. So actually, if you make this approximation, that basically amounts to replacing this px here with basically, something which, just assuming that it doesn't depend, you take away this h dependence here. Okay, so if you do this, you basically find another diffusion equation here. So actually I generalized it to, you can generalize this for a varying d of x. What happens is that you actually find a drift term here, okay? And this entropic drift term is just equal to minus t times log of h of x. So actually, even if you didn't make this approximation, you can guess how this happens, right? Because you know that if you h of x, sorry, h is the height profile. So h is the total width of the channel. So it's the difference between the top and the bottom, okay? So you can see that, and this must be the case because you know that in equilibrium, okay, you're more likely to be in a region because the equilibrium distribution is flat in two-dimensional space, right? So you're more likely to be in a region where the space is big. So this is just a purely entropic trapping effect, okay? And actually, once you do this, I mean, you can use something like the Lifton-Jackson formula. So if you started off with a two-dimensional problem, you've reduced it to a one-dimensional problem. And so now you can just apply this formula here for diffusion in one dimension in a general potential. Okay, so you get this formula here, and you actually find this classic result. The effective diffusion equation, effective diffusion constant is just given by the bare diffusion constant divided by the spatial average of the width of the channel and in the denominator multiplied by the average of h to the minus 1. Okay, so this is a well-known formula. So this shows you that the diffusion will be slowed down. So even though the Brownian particles don't really feel any obstacles, this entropic effect, when you look at the marginal distribution, you're more likely to be in the middle of the channel where there's more space. So that's where it comes from. Okay. So actually, how can you improve on this? So actually, I mean, people have worked on these problems for a long time. And actually, in most of the literature, there were methods that were used. There were methods where people try to carry on generating an effective diffusion equation. But actually, there's a formalism where you can basically work out what the effective diffusion constant is. So you can actually, I'll explain a bit later, you know, a slightly more complicated example, how you get these formulas. So basically what you end up doing, you have this f, which is called an auxiliary function, okay? This function f, so these depend, in general, if you have, you know, if you have a system in higher dimensions, okay, you have fi, fj for each spatial dimension. This obeys the Laplace's equation. There's an orthogonality condition, and there's an effective boundary condition on this f. So basically, if you can solve this equation, you can directly compute the diffusion constant, okay? And so these formalisms are very useful because when you look at lots of the literature on these channel problems, people simulate them numerically, and it's actually quite difficult to simulate. If you have very jaggy channels, you can imagine that it's very difficult to simulate. But if you actually use these formulas here, you can just take a PDE solver. You don't have to do any numerical simulations. Okay, so but the problem is you have to solve these equations, okay? So actually you can find these sorts of formula. I mean, there's a very general macrotransport theory by Brenner and Edwards, okay? And there are also Kubo type formula. So there's a more sort of stat-mech. So this comes from more fluids literature. This is a more stat-mech approach. And actually in the case of no drift, actually, you can use the Stokes-Einstein relation. And if you use the Stokes-Einstein relation, I'll show you a very easy way of understanding how this comes up. So you have to solve these equations. Now, if I look at a channel which has a reflection symmetry, so now I have to work out these functions. I have f of xy is equal to f of x minus y. So y is the height direction. I have the periodicity, okay? And then this is the formula. Actually, if I plug in this formula, if I can compute this function h, I just have to do this integral here to calculate the effective diffusion constant. So actually, so how do you go beyond the fixed Jacobs approximation? Well, in 2 dimensions, there's a very nice way of doing it. You can basically, because you have Laplace's equation, you can write this function f as the real part of some function in the complex space, okay? So you can write it as w of x plus iy plus w of x minus iy. And the boundary condition, actually, remarkably, when you write it down, it looks like this. You can actually integrate it. So it actually tells you that this function, the difference between this function evaluated at the top and the evaluated at the bottom is just equal to 2i times h of x plus a constant, okay? And so actually you can generate the perturbation theory if you basically, so if you take this equation here, you can basically set L to 1. If you set L to 1, that means that the small parameter, which is h divided by L, is in this variable epsilon here, okay? And so if you take this formula, you can basically expand it in epsilon, and it gives you this, okay? And so then you assume that this W has this expansion. Actually, you can show that you only have even powers of epsilon, which is rather interesting. The constant has this form in terms of odd powers of epsilon, and you can basically crunch this thing through. Okay, and so actually using this, so this avoids, you can do it using the lubrification approximation as well, but using this complex analysis method, you can push the perturbation theory to order epsilon 4, which was done using this method of writing down an effective diffusion equation. So you actually show that this more rigorous method agrees with this, this method based on writing an effective diffusion equation. And actually you can even push it on, you can even calculate the epsilon 6 term. Okay, so you can push this a long way. Okay, so now the interesting thing is if you look at this formula, so this formula here, this first term is just the fixed Jacobs approximation. This term here is the first order correction, which was computed by lots of people using different methods. Now the thing is you can't really see it, but actually it's because of my type, but you actually start getting derivatives here. There's something quite interesting because channels don't have to have a smooth derivative, right? You can have so I'll come back to that later and we'll see what happens when there's a discontinuity. And so actually what happens is that if you look at how this perturbation theory works, so if I take this as a sort of bumpy sinus, a sine, cosine type channel, you can see it often in these problems, what you can see is when you look at the perturbation theory, you can see that as you change the perturbation theory, it overshoots and undershoots, okay? So you can see how the perturbation theory is working here. So this is the second order. This is the exact numerical result. You see this thing is starting to fail third order. So at a certain moment, you know, these expansions, they can only work so far, but we're going to quite large values of epsilon. So actually what people hadn't looked at was what happens for large epsilon. So large epsilon, you don't have the lubrification approximation, but you can come up with a very simple argument. Now, if I look at this very jaggy channel, okay, you can imagine, so the only time, if I'm here, most of the time I spend here, it's actually wasted, right? Because I can't diffuse anywhere. So the only moment where you can actually disperse is if you're in this volume here, which I've called omega prime, okay? So it's in this free part of the channel. So basically the argument would be that x squared of t would go like 2d times tau of t, where tau of t is the time that you spend in this channel up to time t, okay? And so a basic ergodic argument would then tell you, well, okay, if this omega is the total volume of the unit cell, then tau of t is just equal to omega prime divided by the total volume, okay? So this is true, but if you look at the processes on the unit cell, okay? So this is what you find. So this tells you that D effective should be equal to omega prime divided by big omega times D0, which gives you this formula here. So this is, now the interesting thing is that this is clearly a lower bound, okay? Because actually you can do it, you know, you're not, if you, I mean, I'm saying that you can only diffuse here, but imagine if you're here, you can do some useful diffusion as well, right? You're not necessarily going to be trapped high up here. So the question is, can we show that this argument, this intuitive ergodic argument is right? And actually what happens, you know, is there a correction? So this is the result as epsilon goes to infinity. What's the result for finite epsilon? And so actually what you can do is, I won't go into the details, but you can basically, if you look like something like a septate channel that has this form here, you can actually make a conformal transformation. You can convert the Laplace's problem that I was telling you into a sort of electrostatics problem that you might give to ambitious undergraduates, okay? And so what you actually find after doing this calculation is that the effective diffusion constant, so you can calculate this first order correction in 1 over epsilon. And actually, this turns out to be universal. It's independent of the form of the channel above here, because basically what's happening is it's because locally the channel, you know, it's going up and it's making some loop here, but actually the local structure at the bottom is responsible for the little bit of diffusion it gives an extra. And actually what turns out is, so this is the ergodic calculation, and the 1 over epsilon result actually turns out to be sort of almost universal. Okay, so you find this log 2 over pi, and then this is just the average of the height profile. Okay, so this is the first order correction. Now, Of course, in the literature, people have been trying to come up with better and better approximations. You know, physicists tend to do perturbation theory, then we try to exaggerate it and make it work better. So actually, this is for another sort of wiggly cosine sine type channel. And so the idea is actually, if you take, so this is a Zwanzig approximation. This is Rigara-Ruby. This is Kelleny-Perkus. And basically, these are all resummations of effectively the order epsilon squared result. Okay, and the reason they were doing this resummation of the order epsilon squared result is they wanted to apply it to channels which had a discontinuity. Okay, and you can see. So what you can actually do is you can take the perturbation theory and you can actually make it agree with the large epsilon result, okay, using a Paddy resummation. So you can actually see here, you can basically get a result which agrees with the whole of the range. Okay, so the problem is that all these approximations, they don't go to the large epsilon limits, so because they're only using information about the small epsilon result. Okay, so let me come back to discontinuous channels. Okay, so as I said, some of these resummations were motivated by the fact that you find that there was a zeta prime in the perturbation expansion. Okay, so what happens when zeta prime is infinite? So you can see you have various types of discontinuities that you can write down. So you can have things that look like this, or you could even have like a little shutter that comes in, right? So this is a continuous channel, but it has a little barrier that comes down here, or you could have a combination of both. Okay. So actually, the remarkable thing here is that you can actually show that when you do the calculation here, really the reason the second order perturbation theory is diverging as it was done before is because actually now in this limit where things are sharp and discontinuous, the correction to diffusion is actually order epsilon. Okay, and basically, so the formula is, so this is R, I've now changed, this is basically just the radius of the height of the channel, the width of the channel. So this is what I was calling H before. This was the length. So you can see this term here is scaling as order epsilon, okay, through this term here. And then you have these universal terms here, mu, which basically depend, which take these forms. So this is this sort of discontinuity here. So it has this form of correction. This, this sort of like, this discontinuity of this type here has this correction, and this discontinuity where you just have a little, sheet that comes down to block you has this correction here. And actually, if these are separated by distances which are of order 1, they just add up. Okay, so this is basically, so you shouldn't resum the perturbation theory in some ad hoc way because actually it breaks down. Okay, which is actually quite strange, right? Because you would think you should be able to approximate these sorts of objects, using some functions and smooth them out. But when you do the calculation, you find this. Okay. So actually now the second part, I was ignoring the effects on the surface. I was ignoring the effects of interactions with the surface. Now there's this paper which appeared in Physical Review Letters. So non-monotonic diffusion of particles among larger attractive crowding spheres. So actually what they did in this simulation is they put a load of hard spheres which were not moving, they froze them, okay? So you can see it looks very dense here, okay? And so in between the spheres, you have a Brownian particle, which you can adjust the size of the spheres. You can imagine it as being a point particle, okay? So you have this particle which is diffusing here. So this problem of particles diffusing amongst hard spheres, this has been studied, this goes back to Maxwell actually. The diffusion constant is related to the conductivity. And sort of you can find lots of conductivity or dielectric constant, okay? So basically it's almost the Maxwell problem. Here they have a random configuration. So this is the radius of the hard spheres plus the radius of the particle, you can see. So this gives you effective hard exclusion. Okay, and then what they basically did is they took a sort of attractive exponentially decaying potential and they put it on the surface, okay? And so basically what happens there is that the spheres, they're not just hard spheres, they're actually weakly attracting the particle. So the particle can actually come and get stuck on the spheres, okay? So, so if I draw it, so you just have this, so it's normally the hard sphere problem. So a Brownian particle, tend to be attracted here, okay? Now, when I first saw this paper, I really thought it was wrong, because you see they actually showed that the attraction, so you can see this, so this is phi is the volume fraction, and this is epsilon, okay? So this is measuring how likely you are to get stuck to the surface of the sphere, okay? And so basically what happens, so what they're doing is they're increasing epsilon here as a function of the volume fraction. You actually see here, look, you see that the diffusion constant increases when you get stuck to the surface of the sphere. Now, it's like, I don't know, probably lots of people think that can't be right, okay? But it's actually right, and it's right in a very subtle way, right? It's clear that if I get stuck to the surface of the sphere and it's too strong, then I just will never leave the surface of the sphere. So if I take the limit epsilon goes to infinity, I'm never going to go anywhere. Okay? And you can see that the effect becomes, obviously the effect is becoming more important at higher volume fractions. Okay? So this weak attraction leads to an increase in diffusion, which is, I personally found, a very intriguing and interesting result. Okay, so they did, and so this happens for disordered sphere configuration, the numerical simulations for disordered sphere configurations and for ordered sphere configurations in 2 and 3 dimensions. So actually, let's have a look at this model. So so we're going to write down a model now. So for our spheres, I'm going to have 2 equations. I'm going to have a bulk equation. So I'm going to have ordinary Brownian motion. I've put a drift in here in the bulk. So you can see these are the trajectories. And I have a reaction with the surface. So if I look at the surface equation, basically what happens, I have diffusion along the surface. So these are the gradients. These are the gradients associated with the surface. And basically the terms here, so when I'm on the surface, there's a KD, which is a desorption parameter. So I can leave the surface and go into the bulk. But this is the local bulk concentration just by the surface, and this is an absorption factor. So this is like a chemical reaction. So you sort of absorbed onto the surface and you can absorb off. And in order, the correct boundary condition, which you get from conservation of probability, is just this, that the flux is just equal to this object here, okay? So this is the basic model. So instead of having a potential of finite extent, you know, it's like, you can think of this as being like some sort of delta function potential. Okay, so when you're interested in these sorts of problems, okay, let me write down explicitly the dispersion coefficient. So this is basically the effective velocity. So this is just x of t minus x of 0 divided by the total time. And this is what the diffusion constant would be given by, okay? So actually, the easiest way to derive the relevant formula to compute the dispersion is to take the Stratonovich formula for the effective drift. So this is a classic formula, easy to show, where these are the currents associated with the Fokker-Planck equation in the bulk and on the surface. And then basically what you do is you apply a force. This drift term here that you apply is basically related for the surface and then a bulk, and it's just what you would get if you applied a uniform external force to the system, okay? So basically all you have to do is compute this effective drift, and then use the Stokes-Einstein relation. And so actually I won't go, so the perturbation theory is quite easy because you can actually see the bulk. You can actually work out that the bulk probability distribution is just uniform. The surface probability distribution is uniform, and it's related to the bulk by this. There's an effective length given by the absorption and the desorption coefficient. V is the volume of the bulk, S is the area of the surface. So basically what you assume is that the new steady state probability distribution on the periodic cell is given by the old one plus a correction which is of order F. You do perturbation theory on that, and you basically, so this is easy enough to compute. The effective diffusion constant is given just by this formula here from the formula I wrote down for the drift, taking the derivative respect to the small force, and you basically derive these auxiliary functions. So this is, obviously, you can generalize this to systems which are not in equilibrium, that don't obey detailed balance, but these are the equations you basically have to solve. So you have a bulk Laplace's equation. This is what happens to your surface equation, and you have a surface boundary condition. So these auxiliary equations look very similar to the equations for the probability density function. So if you look at hard sticky spheres on a cubic lattice, actually, so there are methods of, I won't go into the details. So if you look at, there's an expansion you can make in the volume fraction, which you can push to quite high orders. And basically what you find here is that the effective diffusion constant is, you have an explicit expression for it. And actually the surface absorption effect is actually occurring here. So one of the things that the authors of the Putzel et al. Didn't look at is the diffusion constant they had in their problem was the same as the bulk. The surface diffusion constant was the same as the bulk diffusion constant. That's clearly not very realistic, because you know that if you go to a surface, there are hydrodynamic drags which increase, and so the diffusion will be slower on the surface. So here we have the surface diffusion constant, okay? And so you can see that basically the chemical reaction rates are appearing here, okay? So this is the formula you get. And actually, so if you look at the, so this is, we tried to mimic the Putzel simulations. We didn't have an exponential distribution, but we basically, took our surface interaction to give the same equilibrium distribution near the surface, okay? So you can see it fits their data, and it works remarkably well, actually, in terms of this, this delta. And you can actually see, so you do get this maximum. It's quite a small effect in these regions here, but you generically get this. So basically what happens is that for small delta, the diffusion constant increases. So what you can do is you can take the formula that I wrote down. You say, actually, calculate the derivative at 0, look at when it's positive and when it's negative, right? And you can actually show that you can have an increase in diffusivity for small delta as long as the surface diffusion constant is bigger than this value here, okay? So it's bigger than this, what I call D star S. So you can see that, and it's remarkable because it doesn't depend on the reaction rates. It only depends on the volume fraction. Okay, so this is a way of predicting when the diffusion will be increased at small delta. So as I said, the effect is relatively weak, but you can now, if I look at the problem of channel geometries, you can do something similar now for channel geometries. So this is a more systematic expansion. So you basically say that you write down an expansion. So if you, in terms of 1 over L, where L is the period of the channel. So you write that the bulk auxiliary function takes this form. You have a similar form for the surface auxiliary function. Okay, and you plug this into the formalism. You do the perturbation theory. You take the limit L goes to infinity, and you find this result here. This is the formula for the effective diffusion constant for a channel. Where here, this is so D is the dimension of the space. Okay, so it's so for D equals 2, it's a flat channel. For D equals 3, it's going to be a cylindrical channel. Okay, okay. But actually, the interesting thing, there's a nice. I was talking about this intuitive argument for the Fick-Jacobs approximation. So let's see if we can understand this without going through all the algebra. So let me think. If I let me imagine a particle in my channel, and let me fix its position x along the channel. Okay, so I'll do this. So let me think, imagine it equilibrates. So I'll do some equilibrium statistical mechanics. So if I fix, so this is like the partition function for this particle if it's fixed at this position x here, okay? So I write down this partition function. So this is now, this integral dr perp is basically the integral over this line or surface here, okay? And so, and imagine now that I have a potential which is V of x, which is close to the surface, okay? And it's close to the surface, and it's equal to this Vs, the surface, and it's only non-zero at a distance less than little l from the surface. So what I'm saying here is that I have some sort of little, region here of thickness L where it has a non-zero potential. So when I do this integral, you can see this is just a purely geometric integral. So this is just coming from this is basically just the surface area of this disk here, okay, which is the entropic term. And then you're getting a term which is coming from the integral on the edge of this. So this is sort of a bulk term in the middle, and this is just coming from the integral on the surface, okay? So normally this term, if I didn't have this interaction with the surface, this term wouldn't be here, okay? So this term here would give me the Fick-Jacobs approximation for general D. Okay, so so this is what the Z of X looks like. And now what you do is you take the limit where L is going to 0 in such a way that L times the exponential of minus beta times V of S is equal to delta. So this gives you the correct surface equilibrium distribution, okay? So now if you look at this and you say, well, actually, so if I fix X, what's the free energy or the effective potential that this particle is seeing? Well, you just take minus 1 over beta times the logarithm of this object here, okay? So this is the object that you're finding. You can see that, so the delta is appearing here. Now, the other thing is if you're assuming, the Fick-Jacobs approximation is assuming that the system is equilibrating, okay, quickly enough in this region here. And so that basically means you would say, well, okay, so I should basically calculate the average effective diffusion constant in this region here, okay, with respect to this Boltzmann weight. Okay, so if I calculate this with respect to this Boltzmann weight, you can see, this is, I'm just looking at the, it's easy to see that this is just the bulk probability, this is the surface probability, right? So when I do this computation, I just find this term here. So you see the surface diffusion is appearing up here, and the bulk diffusion is appearing up here, okay? If I take the limit delta goes to 0, I just get dB, okay? So now I'm assuming this is the average effective diffusion constant. So now if I use this Lifson-Jackson formula, I basically find that D effective is given by exponential of minus beta F divided by the average value of exponential of beta F times the average value, times the inverse of this average diffusion constant. And it gives you exactly the result we had here, okay? So there's a nice, otherwise, basically what you do here is you just basically doing exactly the same sort of lubrication approximation that we do before, okay? And you can see, so this, I don't know how my students managed to invent this channel, but this is the function to give, so they wanted some sort of ratchety channel, okay? So let's see how it works. So you find this, so if you use this formula here, you see that here you have, so this is where the surface diffusion is equal to the bulk diffusion. So what I claim is not very physical, but you can see as it varies, so you can get a range of certain, so you see in all of the cases the diffusion is enhanced. For this particular channel, the diffusion is always enhanced, even as you increase delta. So this is, I mean, in this case, it's just, if you stick to the surface, it doesn't matter, right? Now, obviously, in this case of the spheres, if you stuck to the surface, this was bad for diffusion, okay? But in a channel of this type here, if you get this effect here, okay? And as you reduce the surface diffusion, you get to a regime where, eventually there's a value beyond which there's eventually a value of the surface diffusion where it's so slow, there's no point going onto the surface, okay? And you can actually compute that critical value, okay? And again, it's a purely geometric factor, okay? So if the surface diffusion is bigger than this D star S, which is given by this formula here, then you will have an increase of the diffusion. And the nice thing is actually this factor here is less than 1, okay? So you don't have to diffuse quicker on the surface than the bulk. So you can get away with this effect here, okay? So you see it's actually quite, so one of the things, I mean, obviously, if in a channel like this, you can see there is a why it's useful to get stuck to the surface, right? Because it's a way of getting you through bottlenecks. Okay, but the interesting thing is it's clearly, so there has this interesting non-monotonic behavior. You see, as there's a certain region where it's no longer interesting to be stuck on the surface. Okay, so you get a lot of variation. So I'm going to stop there, I think. Okay, so that's the end. Thank you for listening. Congratulations to Deepak. And again, thanks very much for the invitation. It's really great to be back in India again. So thank you.
Thanks, David. Questions? Yeah.
I have a quick question. So you showed all these channels, right?
Yeah.
So this perturbation expansion, does it also work if you have overhangs where now people, it might get stuck there, right? And then
so for overhangs, the parameterization is obviously not working, right? The ergodic argument works for the channels, but it's true. The overhangs, it's
even with a force, because now it will need a time to come out of the trap, right?
That's right. Yeah.
So this enhancement of the diffusion in the intermediate, I guess in the last, I mean, you talked about both with respect to interaction energy as well as the channel width, right?
Right.
So there's some work in other contexts where that enhancement happens as a function of the relative size of the pore to the diffusing particles. But in your case, these were, I didn't quite catch whether these were point, I mean, the diffusing particles were point particles, right?
Yes, but I mean, you can, okay, they don't have to be point particles. You can say, you could just redraw the channel, right? If the particle has a finite size, you say the effective channel basically just changes.
Yeah, except this maximum diffusivity is happening at some finite value, that is some value away from the size of the particle, whichever way you do it.
Yeah, actually, I should look at, because the size of the particle is in the formula, right, with the volume fraction. So you'd have to, you have this effective ds, right? This d star depends on the geometry. So the effective size of your tracer is in there, right? Because the volume fraction, the effective.
So it is there.
Yeah, it is there. Yeah. So the effective size of your spheres depends on the size of the tracer particle, right? So there is something in there. Yeah.
So sorry, quick. The other question in the ratchety channels that you showed, I guess you chose it for some reason, but you're looking at diffusion only in one direction then, or I mean that shouldn't.
Well, no. There's actually, so they. I mean. So
why was
yeah.
It
I mean, my students came and showed me this thing, and I said, "Where did you get this?" And they said that they, people who were looking at ratchety type channels where you have ratchet effects when you have non-equilibrium systems had come up with these things. And I said, yeah, well, let's use that because it looks. I mean, it just looked quite cute, right? It was, but obviously, but the interesting thing is, and if you look at the literature on this thing on diffusion in channels, is that there's an awful. Can you imagine doing the numerical simulation of these sorts of things, right? It's very complicated. So actually these transport equations, you can take even somebody who's old like me can learn how to use a PDE package and solve these equations, right? And it gives you it gives you solutions which are clean. They have no numerical errors whatsoever. And when you're looking at narrow channels and you're trying to do reflection, I mean, imagine trying to do reflecting Brownian motion in a discontinuous channel. It's non-trivial to do the simulations. I mean, my students did some simulations, but they took more time than, getting the simulations to work took more time than doing any of the analytical calculations. So these sort of Kubo type formulas are really useful.
More questions? Okay. If not, let's thank David for a very nice talk.